Alright, this is going to be our first video for Chapter 11, titled Intermolecular Forces and Liquids and Solids. So we'll first start by talking about what a phase is. A phase is a homogeneous part of a system in contact with other parts of the system, but separated from them by a well-defined boundary. You might know the phases of solid, liquid, and gas. Those are examples of them. So if you think of ice, you think of a solid phase and a liquid phase in touch with each other. We've learned about gases. Now, gases aren't really what we're going to be focusing on in this chapter because we're looking at intermolecular force. The reason why we're not going to be focusing on gases is because intermolecular force, being the force between molecules, is very minimal in gases because their density, as you can see from this chart, is very low. Liquids, on the other hand, have very high densities along with solids, all right, and they're mostly incompressible. So what are intermolecular forces? Intermolecular forces are attractive forces between molecules. Now these are slight attractions that you'll, well, not slight, but attractions that you'll see between molecules. And then there's intramolecular forces. These are the forces between atoms within a molecule. Now general rule of thumb is intramolecular forces are going to be stronger than intermolecular forces. This can be seen in water. It takes 41 kilojoules to vaporize 1 mole of water, and take that solid water and break it apart from itself to go into its gaseous form. Whereas to break the actual OH bonds in a mole of water, it takes 930 kilojoules. Now, a measure of intermolecular force, we're going to focus on intermolecular force, is boiling point or melting point. You can think of boiling point, the more attractive forces there are within or between two molecules, the harder it's going to be to pull them apart. So the harder it will be to take the liquid form and break it apart into a gas. In terms of a melting point, the higher the intermolecular force, the higher the melting point. The harder it is, it's going to take it to a more ordered state and bring it to a liquid, a less ordered state. These delta H vape, delta H of fusion, and delta H of sublimation. These are energies associated with vaporizing, melting, fusing, freezing, and subliming, going from a solid to gas. So we'll talk about those measures, but those are typically how we measure the strength of intermolecular force. We're going to start with a couple of different types of intermolecular forces. You're going to have to be able to identify and differentiate between these types. The first is between a dipole and a dipole. So these are forces that are permanent, and it's between two polar molecules. So polar molecules have a direction of charge. There's a positive end and a negative end. If you put two polar molecules next to each other, they'll orient with one end attracting to the other of opposite sign. There's another type of force. It's an ion dipole force. So an ion dipole force is an attractive force between an ion and a dipole. So an ion, like this case, is sodium ion, would attract to the negative pole of this dipole, represented by this graphic. One thing about this type of force, though, is you can talk about the relative strength between ion dipole forces, like that in sodium and magnesium. Magnesium, according to Coulomb's law, the greater charge given the same radius, would have a stronger interaction because it is a cation of higher value. It will interact with the negative portion of water, as you can see here, in a stronger way. Another type of intermolecular force is a dispersion force. Now, a dispersion force is not between, or not felt between, well, it can be felt between molecules that are nonpolar. Molecules that are nonpolar can have what's called temporarily, now emphasis on the word temporarily, induced dipoles. So something that is normally not a dipole can have temporarily induced dipoles. Now, there's a couple ways to do that. There's ion-induced dipole interaction. If you imagine this red blob over here was just a representation of electron density. As soon as you put that electron cloud near a cation, the negative parts of the dipole would start to build up towards the cation because that cation is attracting electron density. Hence, you have an induced dipole. You also get the same thing with a dipole-induced dipole, something that is permanently, polar, put next to something that is nonpolar, will induce a dipole in that nonpolar substance. So these are ion dipole and dipole-induced dipole. You can also have dispersion forces with nonpolar things interacting with other nonpolar things. Now, if you look at these items as an electron cloud, just by random probability, at any given time there is a likelihood that there'll be electron density that builds up in one region and electron deficiency that will build up in another region. Temporarily, there'll be dipoles even in nonpolar substances. Those temporary dipoles can interact with other temporary dipoles in surrounding molecules. That is a dispersion force. Now, that ability to have a temporarily induced dipole or to have electron density increase or decrease in certain regions is called polarizing something. Polarizability is the ease to which that electron distribution can be distorted. It can become uneven. It can form a dipole. Now, among dispersion forces, that ability to form that dipole increases when you increase the number of electrons and you have a more diffuse electron cloud. It's more spread out and there's greater number of electrons. You can see in these compounds here, they're all tetrahedrons and they're all nonpolar. And their melting points change. Why do their melting points change? The force exhibited amongst these compounds with each other are that of dispersion forces. As the molar mass increases, the number of electrons increase, and the electron cloud gets more diffuse as you go down, the melting point increases because it's increasing that intermolecular force. Dispersion forces usually increase with molar mass. So I can ask you to identify the type of intermolecular force. And if given a dispersion force and a couple of compounds, I can ask which of them exhibits greater dispersion force. You would look for the compound with the greater molar mass. Okay? If you're answering relative, trying to compare dispersion forces to dipole forces, you can't really compare because it all depends on the molar mass of what you're dealing with. Maybe dipole forces are greater, maybe dispersion forces are greater. It depends on the molar mass. So let's just go ahead and identify the types of intermolecular forces that could exist between these pairs. In A, HBr, in B, Cl2 and CBr4, C, I2 and NO3 minus, and D, NH3 and C6, H6. So right away, I'm going to see that hydrobromic acid, and hydrosulfuric acid, those are both polar molecules. So the intermolecular forces that are going to be present between these two are going to be dipole-dipole forces and dispersion forces. Because they're both dipoles, they can interact with each other. But there'll also be dispersion forces because electron clouds are moving around and interacting with each other. In the case of B, diatomic chlorine and carbon tetrabromide, those are both nonpolar. So the only thing that they can exhibit in terms of force between their molecules is the dispersion force. In part C, I2 is a homonuclear diatomic. It's nonpolar. but the nitrate ion is an ion. So you can have an ion-induced dipole as well as dispersion forces. In part D, ammonia is polar, and C6H6, that is nonpolar. The forces between them are dipole-induced dipole forces as well as dispersion forces. So we've covered dipole-induced dipole, ion-induced dipole, dipole-dipole interactions, and dispersion forces. There's one more type of intermolecular force that we must point out, a very strong type of intermolecular force, an intermolecular force of marked strength because of the atoms involved. This is the hydrogen bond. You'll learn about it much more in biology next year as well. The hydrogen bond is a special dipole-dipole interaction between the hydrogen atom in a polar nitrogen-hydrogen, oxygen-hydrogen, or fluorine-hydrogen bond. All right, so if you have a hydrogen directly attached to oxygen, nitrogen, or fluorine, you can have a hydrogen bond. So you can either interact intermolecularly. This is showing a hydrogen-oxygen exhibiting a hydrogen bond on two separate molecules. This is showing a hydrogen and a nitrogen, hydrogen-oxygen, and hydrogen and fluorine. Now, one thing that we could ask is, I'll ask it right here. Well, we'll first start with, why is hydrogen bond considered to be a special dipole-dipole interaction? Like we were talking about earlier, intermolecular forces typically increases with molar mass. If you go to group 6 in the periodic table, oxygen's group, it goes oxygen, sulfur, selenium, and tellurium. Molar mass increases as you go down. You can see that these three kind of follow suit, and their boiling point increases. Their intermolecular force increases with increased molar mass. But why is water and its group 7A counterpart, hydrogen and fluorine, and group 5A counterpart, ammonia, have these marked differences in boiling points? They have these special elevations in boiling point. That's because they exhibit hydrogen bonds, whereas all of these do not. So you're normally thinking decreasing molar mass, decreasing boiling point, until you get to that case of hydrogen bonding. So which of these, looking at this, can form hydrogen bonds with water? You really need to take a look at the structure and see which of them has those electronegative elements readily available to bond with the hydrogens present in water. I can see that this first one has oxygen, this third one has fluorine, and this fourth one has oxygen. I don't see either those three, nitrogen, oxygen, or fluorine, present in methane or sodium. And so you can see there are no electronegative elements in methane or the sodium ion, so therefore only these can hydrogen bond with water. Now the question will be, will this be able to hydrogen bond with water? All you're looking for is a nitrogen, an oxygen, or a fluorine that is able to do so. If you're asking about a molecule itself, can it hydrogen bond with itself? That's a trickier question because you need a nitrogen, an oxygen, or fluorine directly attached to a hydrogen within that molecule. And I'll show you examples of that in class.